Okay, so let's cover the theory of the chapter section 4. So first is the definition of a binary operation. So I'm just going to use two symbols for it, and it's essentially it's a function from A cross A to A. That's all it is. Yeah, that's pretty much it. Okay. We have assumptions for the real numbers, and that's basically associativity. So this just means plus or dot, right? Next is commutativity. So hang on. Yeah. Third is identity. So there exists the unique 0, 1, such that x plus 0 is equal to 0 for all x, and x dot 1 yeah, is equal to x for all x. I was confused with something else. Fourth is inverse. This means there exists unique. So essentially, if two variables are satisfying the criteria, then they're both equal. That's pretty much it. All right. Uh, Next is inverses. So for all x, there exists. Is it unique? It should be unique, right? Okay. I think uniqueness is a theorem, though, so I'm not sure. So the book says unique, but I think it can be proved to be unique anyways. So yeah. Yeah. So it's probably a theorem. I can try proving it, but yeah, and the book is saying it as a criteria that there exists a unique inverse y such that x uh, plus y is equal to 0, and y such that x dot y is equal to 1 if x is not equal to 0, right? Yep. Okay. And the fifth is distributive property. Yeah. And in this case, we have right distributive as well because of commutativity. So just writing it down. Okay. Next is about the properties regarding order, I believe, or is it something else? I'll check. It's either order or continuum. Not sure. Probably order. Yeah. So if x is greater than y, then for any z, x plus z is greater than y plus z. And if x is greater than y and z is greater than 0, then x dot z is greater than y dot. And then we have two for orders, and that's linear continuum. So it has the least upper bound property, and the other is density. So for all x comma y, there exists a z such that x is less than y is z is less than y. That's just density. Yeah. So these are the laws of algebra, and these are the properties for an ordered field, I believe, and this is the property for a linear continuum. Yeah. Now we have the definition of an inductive set, which basically means in this book's case, one is there, but zero can also be used to define it, and minus one and minus two, you don't. Ultimately, you just need a bottom. So yeah, a set is inductive if one belongs to A, and for all x in A, we have x plus one belongs to A, right? In set theory, we have if x belongs to A, then the set x union x also belongs to it. That's what we use to define what an inductive set is. And this works out this definition and the definition of natural numbers or positive integers we get from this. Um it has some nice properties. For example, I'm not entirely sure whether it's power set of n or n, but one of these ends up becoming a sigma algebra thanks to that. So y- you'll see it later. But yeah, so this is what an inductive set is, and the set. So we take the collection of all inductive subsets of R. Keep in mind we can only take subsets of something else. We can't just generate it from nowhere. So we take all the set of all inductive subsets of R. Let's say they're indexed by A alpha. Um, and the intersection of all of those sets is precisely defined to be Z plus. Right. So now we're actually defining. It's happening later. Yeah. Okay. So one property is that all of the elements are positive because, yeah. So it contains positive numbers because the set of R plus is real, inductive. Fair enough. And yeah, one is positive, so it's inductive, and yeah, it checks. I don't really have anything to add here. Yeah, we'll do this in the exercises. Then there's a definition of a section, which is nothing too special. Uh, well ordering property, that is, the well ordering property is just everything has a subset, and is there anything new to be covered here? Let's see. Yeah, so I think we'll tackle a lot of exercises that which teach the induction process. So in the process of solving them, I think we'll encounter a lot of them. So the proof will kind of already be covered in the exercises. Okay. Okay. So yeah, it just one more thing that the set Z plus has no upper bound in R because of the least upper bound property, and that's because you take any upper bound of Z, then oh yeah, right. So since this is the least upper bound, this will no longer be a bound, and n must be greater than b minus 1 because b minus 1 otherwise would become the least upper bound, and then n plus 1, which has to belong to z, will be greater than b. So yeah, and this works purely from the order. We're using the order axiom here, adding one to both sides. Yeah, and then yeah, standard notation, which defining what 2 and 3 are, and yeah. For proving strong induction and weak, no. So weak induction is just the property which will be proven there. For strong induction, it's I try to cover it with the exercises. Yeah, along with the proof of the weak, the well ordering principle.